So this is joint work with George and some other people, with John and Victor from Liverpool, and Andreas and Sam from the HPI. I talk about basically the same problem as the talk before, like about temporal exploration, just in a slightly different model. Because I will try to use randomness to explore the graph faster instead of having frequent edges there. I will skip the introduction a bit short because I just heard about what exploration and temporal graphs are. So I don't have to go too much into detail. So the idea is you have some network, you want to visit all the vertices, like for example, taking the train to go to all the cities in Europe or something like this, and you want to do this as fast as possible. So the idea is you have some underlying graph. We heard before that there are multiple ways of presenting temporal graphs. I will use the snapshot version, so where I show you the graphs one by one. Remember that this is a temporal graph, so the algorithms that solve this problem are given the entire sequence in advance. I will not show you the entire sequence in advance because this will be too much information to pass. So I will just show you snapshots one by one. This is just an example for exploration on the static graph, where the underlying graph doesn't change. So in each step, you have the exact same graph, and in each step, you can go over one edge to explore the entire graph. And you want to explore all vertices and do this as fast as possible. And as you saw before, what is true for static graphs and also for the frequent edges, you can explore static graphs in linear time by just taking any tree and just traversing the tree back and forth within 2n-3 steps. So what we do now is we look at the temporal problem. And what we assume is just that in each snapshot, the graph is connected. Like before, we didn't need this because we had the regular edges, but then we needed that the underlying graph is connected. If we don't assume that the edges appear regularly, we kind of somehow need that you can go from everywhere to everywhere else. So we assume that in every snapshot, your graph is connected. And throughout the talk, I will more or less assume that your graph is actually a tree. This is because I look at lower bounds, so how long it takes to explore the graph. And trees are basically the worst case for this, because if you have more edges, this just gives you more choices on where to go, so this makes the problem easier. Meaning, if I want to give you some lower bounds, then trees are basically enough to do that. I have here some reminder of what has been done before. I will not go too much into detail. Basically, this problem has been introduced in like 2014. It has been shown that it's quite hard to solve it exactly. But that if the graph is always connected, you can definitely explore different n-squared time steps. The reason for this is that you can basically go from anywhere to anywhere else within n-1 steps. And then if you do this n times, you can explore the entire graph. And then later, Erlebach, Hoffman, and Kammer basically showed that it's even harder than you saw before. Like you can't even find an n to the 1 minus epsilon approximation. They also showed that this n-squared is basically tight. So there are temporal graphs where you actually need n-squared snapshots in order to explore them. And they also looked at some regularly present edges before and what those do. And then later there has been a bit more work on basically finding some restrictions on the graph so that you don't have this n-squared lower bound. Because if you need n-squared snapshots to explore the graph, this is kind of annoying. So there have been some restrictions, like restricting the graph to planar, or restricting the number of edges, or restricting the tree width of them, or something like this. And in this talk, I basically try to not restrict the underlying graphs, but try to see what happens if I introduce randomness to the model. And basically try to get down this n-squared lower bound by getting rid of basically what the adversary can do in order to make the problem hard. And for this, I first want to go through an example of what the adversary can do to make this problem hard by basically showing you this n-squared lower bound. And again, we want to explore this graph. And we start at vertex V. And in the first snapshot, we can just go to A. Then in the next one, the graph changes. And this example might be familiar because this has actually been on the slides in the previous talk. Like we have a star, which started at A, now is at B. now it's at C, but now it doesn't circle around again, now it goes back to A. And now I have two people here. The reason for this is that, as I said before, this is technically a temporal graph, so you're supposed to know all the snapshots in advance. But if I don't show them to you, then basically right now you can't use the information of what the next snapshots are in order to decide where to go, but the algorithm can. So what I normally do is I decide non-deterministically which way I go. So in the previous step, I was at C, and now I want to visit a new vertex that I haven't visited before, but in this snapshot, I can only go to A, and I've been at A before. So right now, I kind of don't want to decide whether I stay at C or I go to A, because without looking at the next snapshots yet, I don't really know what's better. So right now, I just have two of those figures to show you where you could be right now. And now if I do the next step, now B is the center. So no matter where you were before, whether you were A or C, the only way you can go is to B, or you stay where you were. So the set of vertices you could be at increased now, and you could also be at B. And on the next snapshot, C is the center again. So now I resolve the non-determinism, and I see, okay, if I'm at A or B now, I kind of can only go to C where I could have been before, so this is useless. But if I stayed at C the entire time, then I can go to E now. So basically now is the point where I resolve this non-determinism and I say, okay, if I go back, here I was at C, then I decided to stay at C, I kept staying at C, and now I only go to E. And now if you keep going, you see that I'm on the vertex on the right, and if you saw how the graph looks like, is it basically circles around on the left. And now if I want to go from E to any other vertex on the right, the only way I can go is to the center, and then to the next center, and then to the next center. And only when I pick a center again that I have picked before, only now I can go to one of the right vertices. And this is the reason why you need n squared steps in order to explore this graph. Like in general, you have like n half vertices on the left and n half on the right, and the center always circles on the left. And in order to get from any vertex on the right to any other vertex on the right, you need to go to the center that's currently the center, wait an entire circle for this to be the center again, and only then you can go to the next vertex on the right, which takes n half snapshots each time. And you have to do this n half times, so you need like n squared snapshots. Yeah, and basically now we want to get randomness into this, because, I mean, as you might have seen, the only reason for this to take n squared time is that the adversary can decide the exact order to always be the same and always circle around all of those centers, to always let you wait n snapshot. And we want to define a model now which basically doesn't restrict the base graph too much and still lets you explore the graph faster. So how we define the model is we get an input a set of trees. Like in this example, for example, exactly the same trees that we had before, right? Like those are exactly the snapshots that we used for the graph before. But now instead of getting a temporal graph, which gives you basically the order of snapshots, we get a probability distribution. So we give each of those snapshots a probability, like in this case, for example, 1/3 each. And instead of having this temporal graph, it's always cycled through, we create a random temporal graph now by in each snapshot drawing a random graph from this distribution, independently of each other. So the first snapshot might be A the center, then it might be C, then it might be C again, then it could be B, and so on. So now the adversary can't decide in which order they choose the centers, but it's decided by randomness. And the goal of the paper and the goal of what I try to explain you now is to show you what impact this has on the upper and lower bound and how long it takes to explore this random version of the temporal graph. So first, let's see what happens if we take the previous example, so the previous lower bound into temporal in the non-random setting, and see how it changes in the random setting. So again, the hard part is getting from one vertex on the right to another vertex on the right. So let's say this time I want to go from B to D. So again, the only way I can go is go to the center on the left. And now a new random center is drawn. And again, I can only go there. And this will keep happening until at some point I pick the same center again that I had picked before. And only now I can go to D. And as you can see before, I didn't visit A, and now A is actually also visited because on this path I took, I actually also visited A because the actual path that I took was I went to A in the first snapshot, I waited there when C was the center, and then I took the third one to go to D. And you can actually now calculate the expected time that it takes for a center to be picked twice. And the time for this is more or less exactly square root n. The reason for this is that this basically perfectly describes the birthday paradox, which I don't know whether you heard about, but the birthday paradox basically decides, given the number of possible birthdays, how many people do you need with random birthdays in a group so that quite likely there are two of them with the same birthday. And the answer for this is roughly square root n. And it's the same here because the birthdays are the vertices on the left. In each snapshot, I just draw a random one of them and I wait until I find someone who has a birthday, which I already had. So now to explore this graph, you don't need n squared time steps anymore, but in expectation, you need n times square root n because for each of the vertices on the right, you need to wait roughly square root n steps so that you can go to any other vertex on the right. Then you have to do this n times, and then you're done. So we have a slightly more general result where we don't have n half on both sides, but k center vertices. And then you also get this extra k log k term because basically you get a square root k from the birthday paradox. But if you have almost no leaves, like if there's basically no vertices on the right, then you don't have to do this too often. And I didn't tell you how long it takes to collect the vertices on the left, right? Because they happen to be centers quite often. And in order to explore them, you just have to wait for them to be centered, which is much faster than waiting for the duplicate. So yeah, if you basically only have centers, then the time to collect those dominates the time. And this is basically coupon collector, which is also a very known problem, which I don't want to go into detail to because this is basically not that important. But yeah, so if you plug in the number of centers to be like n half, you get n square root n as the lower bound. And now the question is this tight? And the answer is yes. So we show that if you're given any set of trees and any distribution on those, so you can basically fully decide which kind of trees happen and appear how often. Now you draw a temporal graph of this, then you can explore this graph with high probability within 200,000 n square root n steps. You might see here that we didn't quite optimize for constants. The proof is quite complicated, and over the multiple lemmas, the constants keep stacking up. So yeah, this is probably not tight constant-wise. But yeah, so this is what we show. And I should want to give you an intuition on how this proof works. And for this, I first want to define what closed vertices are, because I need this for an in-between theorem. So closed vertices, we say that two vertices are close or are TP close if you draw a graph from this distribution and you look at T snapshots. Now I look at the probability of V being reached by U, and I want this to be at least P. So let's do this in a picture. I, for some reason, renamed the vertices to be U and V now. But I have the vertex U and V. I have T given. So what I do is I draw a temporal graph on the distribution. I look at the next T snapshots, and I look at the sets that I can reach from U within those snapshots. Then I draw another graph on the same distribution, and I get a different set of vertices I can reach. I do this again, and I do this again, and this time you can see it reaches V. And what I basically look for is what is the probability of this event happening, so that V is within the reachability set of U. And I can say that TP close, and the probability of if I do this with these steps is at least P. Now note that TP closeness is symmetric. So if one vertex is TP close to another one, then they're close to each other, which is not obvious at all, because in temporal graphs, reachability itself is not symmetric, right? So just because you can reach V here doesn't mean that V actually can reach U, because this path that I take might be like temporally increasing and might, not be reversible. But because I draw temporal graphs from this distribution and draw each snapshot independently, for each temporal graph that I draw where U can reach V, it is equally likely for me to draw exactly the same snapshots, but in the opposite order. And in this reverted graph, now there's a path from V to U, right? And because I can do this for all the graphs in the distribution, the probability that you can reach V within these snapshots is actually exactly the same as the probability that V can reach U. So this closeness property is actually symmetric, even though reachability itself is not. And what I want to use this for now is to show this theorem. Ignore the constants in there. Like basically, I just want to talk about constants now and just roughly the size. So what it says is if you pick any, you have the distribution on the graph given, and now you pick a fixed vertex V, and you want to look at its square root n closed vertices with some constant probability, then there are at least square root n vertices in there. So for each vertex, there are square root n other vertices, which you can reach in the expected time of square root n. This is actually like the best you can do. Like there are graphs where from a fixed vertex, all other vertices are at least square root n away from them. So in expectation. So it might be that there is no closer vertex than this. So in this sense, this is more or less tight. So for the rest of the talk, I try to first show you why we want this. So how to use this theorem to show the upper bound on the exploration. And then afterwards, I try to give you an intuition on why this theorem is true. So first of all, how do we use this? So we take this set of vertices, and now we connect all the vertices that are close. And as we know from before, every vertex has at least square root n closed vertices. So if I draw the components now that result from this, then every component has size at least square root n, because every vertex has degree at least square root n. Which also means that there are at most square root n of those components. Now, I take a spanning forest, meaning I just delete most of the edges in the components so that I only have the tree left. And then I connect those components with some arbitrary edges. Now, what I have is I have some static graph that tells me something about the distribution. And how I will use this is I will do exactly what we heard in the talk before to explore graph. Like I will take this tree and I will traverse it. What does traversing the tree mean? Those edges don't actually exist in the graph, right? And in contrast to what we heard before, I will not wait for those edges to appear because they might never do. Like some of those edges might never appear in the graph.
How many extra edges do you add arbitrarily?
I mean, as I said, the components are there at most square root n components, so I need at most square root n extra edges.
Is the tree?
I connect it to a tree, yes.
The resulting thing.
The resulting thing is a tree.
Is always a tree?
Yes.
Okay.
I mean, I just want to, basically, by traversing this, I want to reach our vertices. So I just need to connect this forest somehow to do this. So I add exactly the number of components minus one edges. So if I traverse an edge now, I don't actually wait for this edge, but what I do is I start at this vertex and then I look into the future until I see a path to the target vertex I want to reach, and then I take this path. And from the definition of closeness, the probability of this being like of size square root n is constant. And if it fails to be of size square root n, I just wait this time again and so on. So the expectation is actually just square root n long. And this is true for all of those close edges in there, meaning that traversing those bold edges here takes an expectation only like square root n out. So the expensive connections are the ones between the components because those vertices are not close. But as I said before, you can reach any vertex from any other vertex within at most n rounds. So I can definitely go from the right component to the middle component within n rounds. And because there are at most square root n components, I can just do the square root n times and still fall within this n square root n that I wanted to show, right? So now the total time I need to traverse this tree is I have at most n edges, which all take at most square root n rounds to traverse, and I have square root n edges, which take at most n rounds to traverse. So if I take this together, I take n square root n rounds. And this actually holds with high probability because the n steps deterministically just always are at most n steps, and the others, there are so many edges of them that the probabilities basically cancel out. So it's quite unlikely for all of them to take much longer than expected. So you actually get very high probability to explore in this time. Yes, so if we have those close vertices, then we can show that we can explore n square root steps. Now I try to give you some intuition on why this is true. And first of all, I simplify the statement. I just want to show you that this vertex B has one closed vertex, not square root n many. So I'm just looking for one closed vertex. So I know that in each snapshot, B has an edge because my graph is always connected. So every snapshot will have an edge to some vertex. And now I look at the probability of this edge appearing in any snapshot. And if this is more than 1 over square root n, then just waiting for this edge gives me a constant probability for this to happen within square root n rounds. So I'm just done. Meaning I can assume that all of those edges are less likely than 1 over square root n. So there have to be a lot of them because the probability of an edge appearing is 1. So it'll probably sum up to 1. And if all of them are at most 1 over square root n, then they're at most square root n of those. So I have a lot of potential neighbors. So if I wait for square root n rounds of my graph, I actually visit like square root n neighbors, or can potentially visit square root n neighbors. And what I do now is I look at the reachability set of one of those neighbors, or in all of those neighbors. In particular, I fix the vertex u, and I look at its reachability set, so the sets of vertices it can reach in the next square root n steps. And I compare it to the vertices that the other reached vertices from V can reach within the same time. And the first case is basically that all of those sets are more or less disjoint. So if I take this vertex U, then the overlap with the others tends to be very small. What happens then is that if this is true for all of the vertices, then we have those square root n vertices that are reached within the first square root n steps. And each of them have like a set of square root n vertices that they can reach, which are mostly disjoint. And as I said, I ignore constants, so we don't actually use for square root n rounds, but some bigger constant times square root n. So if I union those sets now, I have a set of some bigger constant times square root n edges, so some bigger constant times n edges at vertices. And they are disjoint, right? So I have a set of more than n disjoint vertices, which is a contradiction because the graph just has n vertices. So I can't build any set in this graph which an expectation has like more than n vertices in there. So this can't happen. Meaning that what always will happen is you have some set that overlaps quite a lot with the set of the others. And what I basically do now is I do the exact same procedure again, but at a later time and backwards. So here I started at time 0, right? And I looked at what V can reach. Here I start at time 4 times square root n and see what can V reach in the previous square root n snapshots and what can they reach backwards before that. And I sadly don't have time to go into details for the next step because this is basically the main part of the proof, is showing that those vertices in there, that you can find a subset of those vertices which are more or less independently drawn from some distribution. And basically the idea is that on the left you have U, who can reach some vertices which are also reached by the rest, which are like square root n many, and on the right as well. And now if I draw twice from this distribution of square root n vertices, then as before using the birthday products, there will be with some constant probability a vertex in both of those sets. And now if I have a vertex in both of those sets, in this backwards thing, V can reach other vertices, right? Because I draw from this random distribution again, and this will be a different instance. So in this case, U might not be reaching V. But over this vertex W is in the reachability set of U, so U can reach W. W is the reachability set of the vertices reached by V in this backwards set. So W can reach one of those vertices, and then this vertex can reach V. And all of this happens with constant probability. And as you can see, there's a path from U to V now. So I have shown that with constant probability, there's a square root n path from U to V. So U and V are close to each other. And which was the goal of proof, right? I tried to find the vertex which is close to V. And this is just always the case because, as I said before, the vertices can't all have a small overlap with the rest, so there has to be a vertex which has a big overlap, and this vertex happens to be close to me. Yeah, so this was the idea of the proof. If you want to talk about it a bit more, then feel free to talk to me lunch anytime here. I'm happy to go more into detail because I skipped a lot of steps in the proof right there. We have some open problems. So this lower one that I showed you, Adler, and Hoffman actually gave a more detailed lower bound, which depends on the degree of the snapshots. So in the lower one I showed you, all the snapshots were stars, so the degree is quite high. If you restrict the degree to d, then you actually get a d times n lower bound, which in the randomized setting, using the same arguments as before, gives you a square root d times n lower bound. We actually think that this lower bound is tight. So we think that if you restrict the degree of the graph on your distribution, you can actually show an square root d times n upper bound. But yeah, we didn't manage to do so because the proof doesn't easily convert to that. Like you will have to change a lot of steps. Like for example, this closeness isn't true anymore for square root d. You can build graphs which have a degree of 3, where still to a fixed vertex, the closest vertex is square root n away. So you can't just get the square root d using the same idea that we used before. Yeah, the other open problems are a bit further away, so I don't want to go too much into detail. Maybe the greedy algorithm. The algorithm I showed you right now takes like a tree and then traverses this. You can also do another algorithm which just starts at the vertex and then in each step basically always greedily looks into the future until it sees the vertex it hasn't seen yet and goes there. Like I did in the example in the very beginning. We haven't found an example yet where this isn't asymptotically tied or restriction given. So this algorithm might also solve the square root n times n thing. We don't know. I would be very happy if someone can show this or give me a counter example where this isn't true. This is my talk. If you have any questions, you have to ask.